we're going to transition to grading the first part of section 6. Izzy, Emily, you're proving my point that you can still talk fine, but shush. We are supposed to be talking about word problems. Now, guys, how many problems of homework were you actually able to skip?
None.
Wait, in the comment, I redid it and I said, okay, how many problems did I say you need to add on tonight?
Oh, wait, you said we had to add some more?
So I thought we were honors. Let's go check out Google Classroom really fast. I think I have it on the screen. I told you guys, did you have to do any word problems for homework?
No.
Exactly. I erased them from the main assignment. I put them in the category down below. So if you guys looked at your assignment and if you read the class comment, that's right here. I took away the word problems like I said. And 85, 91, 96, and 101, see, are due when? No, well, I mean, the picture was the normal due this morning, right? But then these extra 4 problems, I just said, and it was on there, and it was on there all weekend, that I'm doing what to them? How am I checking them? Spot check. I'm just walking around and seeing that you do the 4. Now, no, they don't need to be, the extra 4 don't need to be scanned in separately, right? However, those 4 problems, I wonder if, how many examples did we skip on Friday? 1, 2, 3. Oh, so maybe the 1, 2, 3 are supposed to help us for the 4 that you guys missed or were unable to do in homework. I'm not going to be able to necessarily go through all of these. Actually, you know what, Marco and Cassie? I'm not even going to probably be able to finish 1 before you guys leave. So let's go ahead and at least we see what we're supposed to do. We're supposed to look through these 3 word problem examples that are supposed to help you on these 4 missing word problems that I changed out of the required scanned in this morning to instead spot check tomorrow. We're going to finish off class with that. But let's go ahead and grade just because that's something I think we can do before Cassie and Marco leave. That way they have at least 1 less thing to do tonight, or they can skip ahead in the video just a little bit when they come to check it out. So, in our homework spiral, all the way up through number 75, but not beyond for right now. We can grade pretty quickly and see if you guys got stuck on the basic skills, the basic pre-physics with vectors skills. I kind of pulled HPrecalc today because they're starting section 6.1, which means they're only like 3 days behind us, maybe 4 days behind us, which is kind of rough. I guess maybe more like a week behind. But I let them know that they are learning law of sines, law of cosines to basically broaden their ability with triangles, and then we're going to do an intro to physics where like triangles are key, maybe not, like Jaden brought up on Friday, maybe not always law of sines, law of cosines, but triangles are key with this physics introduction with vectors. So you guys are already listing things like initial and terminal points of a vector, multiplication and addition, some of the vector properties that I didn't make you memorize. I didn't even make, I don't think, make you write down. But we did go ahead and get vectors in components form by subtracting terminal minus initial. We got the magnitude by doing square root of a squared plus b squared once we had those components. Remember, once you have components, it can be fast to get the magnitude, just Pythagorean theorem. You see that down below as well. Jaden?
For that one, number 14.
Uh-huh.
Okay, so I got square root of 20, but I didn't know.
Square root of 20. This is Algebra 1 skill that actually we literally are covering today in Algebra 1. Break 20 down to be 4 and 5. Multiplication, you are allowed to split up square roots. Addition, subtraction, you're not. But square root of 4 times square root of 5, square root of 4, I know. Booyah, 2 root 5. And the reason why I'm making a point of showing that, Jaden, and not just being like, it's the same number, is multiple choice on a test will be simplified. Does that make sense? And then, yeah, I'll checking your answer. But it would be the same decimal either way, technically, if you were able to do decimals. Number 22, same dealio. As far as subtracting, it was a little bit more precise because you didn't have a 0, 0 as one of the points. And then Pythagorean theorem. Aha! Someone help me. Maybe you didn't write it down. Where did 8 root 2 come from?
28.
Oh, bigger than 28, because 8 would have come from rad 64. 128. Got it. Sorry, I heard you wrong. You can tell my voice, head, brain, everything's fuzzy. Okay. Number 42, you had components. Ooh, unit vector. Wait, who are they dividing the components of the vector by? Who's this dude?
That's the component.
Yeah, component.
Yeah.
We're dividing components by
By
magnitude.
magnitude.
We're dividing the components by the magnitude to get the unit vectors like our formula showed. Yeah? Okay, cool. And then this is just double checking. Once you have your answer, I guess you could do Pythagorean theorem and make sure it's 1. But it's double checking. This one, terminal minus initial, you were just putting it in components and in linear combinations. Oh, do you guys have little arrows above all of your vectors? If you don't, you're wrong. Oh, that's hard. That's a good call. But in the directions, just think, if they are in this section with physics and the vectors, if they're talking about a lowercase letter, it has to be a vector. Now, if it's like a U sub 1 or a U sub 2, then they're just talking about the A or B components, you're okay. It's just talking about A or B. But if it's like an actual U or V or W, it's a vector. Yeah, good call, because the directions are bold, huh? Tricky. Anyway, vector arrows above everything. And then I think number 72 is your last one before the word problem. So you were just having to do, there was a formula for this, right? Magnitude, cosine angle, magnitude, sine angle. And this would have come from 16 and 3 is 48, root 48 simplified. But if you graphed it, you guys might have actually seen that you should have known what it was just looking at it, because the x component would be 0 and the y component has everybody, which is 4 rad 3. But that'd be a bit more of a experimental discovery, understanding the concept and not just plugging into the formula. Now, do you guys want to peek at 96, even though it's one that you didn't do, and see how hard it is?
No.
Oh, look how short it is. Little baby guys. So not all the word problems are going to be hard. But there are going to be concepts that we haven't totally figured out yet. Alec, I'm sorry, what's up, bud?
I totally got the concepts when we take notes, and when I'm completely lost right now.
With all of your homework, like the evens are all wrong?
Like, I just was really confused on the homework.
Okay, my guess is that there's a lot of new terms. And you might have the concept down as far as what I'm talking about, but when the new terms get thrown at you, your brain isn't quite ready for it yet. A way to tackle that would have been to have your notes open and go find, like for instance, number 42 talked about a unit vector. And in our notes, we literally wrote down, and that's something for you to make sure that you're getting everything down. Sorry, that's the SSA. We literally wrote down a formula for unit vector back here somewhere. So you're needing, right now, you're just trying to get your brain used to these terms. You're going to need to actually go through our notes and say, okay, where did we talk about unit vector? And then you're going to have to kind of match up for right now since your brain isn't quite used to it. Because I think you followed my steps of scaling back, but maybe the term messed you up when you saw it in homework. Does that make sense? I just use that as an example. So it's getting your brain used to it, because scaling back, or maybe even something where you're writing words down as we're doing this in notes, like scaling back, so that if you saw that unit vector direction in homework, for instance, on like 42, then you could have gone to your notes, you could have seen that scaling back. Sorry, wrong one. And then I think your brain would have been like, oh yeah, duh, scaling back, I get it, divide by the magnitude. So I think we just need to get your brain used to the terms, and then you're right, that there are a lot of new things. There's a lot of new notation. These side carets are new. And it was over a weekend, which is hard. You didn't have the pressure of getting it done like Friday night when it was fresh in your brain. So let's pay attention in the word problems today. And if I say any words where you're like, I don't remember what that is, let me know so that we can like build it up again. Is that cool? And like drop by if you can during 7th period if you have like a study hall or something. Yeah, Marco and Cassie, go for it. Sorry, 11:30. You can just walk out.
That's fine. No,
You're good. Have fun. Teach the little people. They're teaching lessons. Cassie's actually teaching a lesson. But Alec, it could be something where if you're like, I don't know how to finish homework, come in, because you can always post a comment and be like, oh, you needed to work with me. Jaden.
Number 49, I did not understand.
Oh yeah.
Like everything was going great for me. That was
I saw it.
Okay, this one was weird because we didn't do an example like it in notes at all, right?
And they didn't have it in the textbook.
Yeah. It was trying to, and Alec, here, check it out, because you did have an excellent grasp, like you were tracking with me all week last week as far as like the vectors. Maybe you and I can build up the concept because everyone else had to kind of make it up on their own. So let's check it, okay? This one says, find the vector v. Oh, Emily was like, hey, everything's bold, so vector v. All right, cool. Let's put that little bloop, bloop. As u, there's another vector arrow right there, and then these guys are vectors down below. Okay. But what was the key? Same what, though? Okay. It's not saying same. What's the other part of any vector? It's not saying the same magnitude. It's saying just the same direction. Hold on. Don't we know a piece of information about this guy and that guy? Magnitude is the same thing as on a picture, length, right? It's the how muchness, but it's shown by length. And then this one, well, component, can't I start from 0, 0, and can't I go 1, 2, 3, and then 1, 2, 3, 4? I can actually show vector u, right? I can show vector u. We have to remember what those components are. Remember, some of your brains might still be thinking it's an x and y and it's a point. It's not an xy point. It's a distance horizontally and a distance vertically. It's a displacement. So 3 to the left, 4 up. Got it. Now hold on. How do I know how 10 relates? How do I graph 10? Because I need to be in the same direction. So don't I know he's going to be on this line somehow? Like he has to be the exact same angle, otherwise he's not the same direction. But how do I know 10? Could I go 4, 5, 6, 7, 8, 9? Can I go 10 up? No.
You gotta go 5.
Can't go 10. Can I go 5 and 5? Hold on, wait a minute. How could I know if I go up 5 and over 5? How could I know what the diagonal length is?
This is the formula.
I could do distance formula, or couldn't I do Pythagorean theorem? Couldn't I do 5 squared plus 5 squared will equal hypotenuse squared?
Yes.
So if I was to do 5 and 5, that'd be 25 plus 25 is 50. Is the square root of 50 10? Okay, so you need to go bigger. Okay, so how about, we said 5? How about 7 squared and 7 squared? 49 and 49 is 80, 98. Oh, I'm so close. Oh, that's a struggle. Well, wait a minute. Why don't I just figure out what this guy is and then do it as him? Because isn't he the guy I'm supposed to be making it the same direction as? So how long is he, and then how much longer to get to 10, right? If I can scale back a vector to be a unit, can't I also multiply a vector to be whatever number I want? So I can scale back, but I can also make big, or make bigger. So who is u right now? How long is he?
He's
4.
He's -3. And he's 4. But how long is he? Ah, it's a 3, 4, 5 triangle. Wait a minute. So if he's 5, then what do I just need to do?
Plug it in.
No. We're talking about scaling. Dividing makes it smaller. Multiply it by. I need to get 10. 2. Ah, so if I double it. There we go. That makes sense if I double it. Because if I double it, the 5 is going to become a 10, right? It's going to be in the same direction. I just need to figure out what vector v. Oh, it says find vector v. Yeah, I don't know vector v's components. So who's vector v? Well, double u.
Oh my goodness.
That's a little thing.
Oh, that was so different. You get a whole fraction.
No, Tasha used one of the formulas.
Oh.
Which I did use the formula though. Which formula did I use?
Pythagorean.
Okay, I used Pythagorean theorem. I said, I don't know. I know that u is over and up, -3 and 4. But I didn't know how long u was, which is what I needed to compare to how long I needed v to be. So then I was like, I don't know this, but I do know that. Well, let's use this by doing the square root of a squared plus b squared. I used the magnitude formula, which is really just Pythagorean theorem, which is really just distance. I said, how long are you, u? Oh, you're 5. V's 10. Sweet, I just need to double. Huh, U to get B. I just need to double the U to get B. So he's kind of putting it all together, that magnitude with length, and who is this guy, and what is his length, so I can compare, so I can make a new vector. So unit vectors were very similar to this question, just unit vectors is scaling back and figuring out how long are you, I need to make you 1, so I'm going to divide everybody by whatever length you have. This one was, well, I want a new vector with this length in the same direction, you still start with this guy. You still figure out how long he is. But once you figure out how long he is, and just think of, oh, do I scale back, divide everybody by 5? No, I want 10. Okay, I better double him. And when I double him, what else is going to double? Everything else. The 4 is going to double to be 8, and the -3 is going to double to be -6. So I can use that little formula that we talked about as far as you can multiply components by a scalar, by a constant, and it just distributes in. Is that okay? So instead of scaling back, we were scaling back. Yeah.
I didn't understand how to do the one with like cosines. I don't know.
Can anybody see one with cosines? 75-ish? Okay. Oh, Jaden, these are using the important form. Well, okay, hold on. You guys want to be inspired? Oh, party poopers.
I'm always inspired by.
I'm never inspired.
Okay. Can you trust me for a second and just answer yes? Okay. I didn't do it last week, and I probably should have because you guys needed it, especially on Friday. But Friday, I had lost your attention for so long anyway. You saw who brought what?
Yeah, Rob fell. I'm like clapping video, got back up and tried to.
In chapel?
No.
Wait, I don't know what I sent you.
Doing the
No,
hurdles.
I got another one.
Jay, you guys sent those,
No.
At track?
No,
Anthony.
Nice.
Not right now. I'm trying to learn how.
No, he tried to and like
Thanks,
he
Jaden.
got back up and they tried to learn.
Can you show me what you're wearing?
Yeah, at the end if we have time. If Miss G allows.
Thanks, Jaden.
What's his first
Oh,
name?
so bad.
Yes! Hey, very good.
It's frozen.
Oh, I think it was the movie.
It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Doing a demonstration. Oh! Ah! It's so difficult sometimes to get thrown outside.
Okay.
Wait, does he actually say that?
Yes,
I don't even remember.
Yes, he
You were
does.
young, you didn't understand it.
So wait a minute.
Whoa.
Both direction, he's committing crimes. Both direction and if they put that definition of a vector in a cartoon,
Slap on.
if they put that definition of a vector in a cartoon, what do you think a vector is more commonly seen as? Components or direction and magnitude? Yeah. We don't think about the horizontal vertical because that's not how we think it. We're just like, no, it's here and it's out there. Whether we're talking about a force that's acting on an object, whether we're talking about a direction of something's movement, whatever vectors are being used for, which can be lots of different cases, they're usually thought of in, ready, direction and magnitude form. But the dilemma is the math is so much easier. The math is so much easier when we're dealing with components. So even though naturally no one really thinks of them as having components, everyone thinks about them as having directions and magnitudes just in context of what vectors are. This math was easy. Up until, okay, the weird like same direction as, got it. But then you guys, some of you started getting confused when it went to cosines and sines. Well, it only went to cosines and sines because it said, well, wait a minute, this isn't the way that vectors naturally appear or occur. They naturally appear or occur in this form. And that's why on Friday I went through all that craziness as far as law of sines and law of cosines. Remember this? I went through it the crazy law of sines, law of cosines geometry way. Because I'm like, what if they give me magnitudes and directions? Can we deal with it? The answer is yes. We just have to be very precise in our pictures and putting vectors with the head to tail to make the final resultant or net force. Vector diagrams are what they're called. And then using law of sines, law of cosines. But then I said, wait a minute, don't you guys like component math better? All you have to do is add, Pythagorean theorem, tan inverse. But you can't add unless you use the formulas. So then, Jaden, when you were like cosines and sines, the only reason they're using cosines and sines is because they were dealing with vectors in their natural state, and they were wanting to put them into component form to make the math so much easier and to avoid the law of sines, law of cosines.
So that was when they used like the U plus V.
Yeah. We were trying to do U plus V in theory if they're asking for the resultant. But you can't do U and V. You can't even think about them in terms of components unless you use the formulas about how to get the A component and how to get the B component, which is always going to be magnitude cosine angle, magnitude sine angle. Basically using the SOHCAHTOA relationship and shortening it into easy to memorize formulas. So when you were asking about all of those, the 60s and the 70s, like all of these, they're giving you magnitudes and directions. They're asking you to, over here in this one, they just said find components. And saying find the, given, yeah. So in these ones, you really were just filling in the components. Who are you? Who are you? Who are you? Like you're just doing A and B using magnitude cosine angle, magnitude sine angle. But down here, now, they didn't say resultant, they didn't say net, but they did use that other word that I mentioned. They used sum. So you're adding the two together. That's when you would take U and do his magnitude cosine angle, magnitude sine angle. I do V's, magnitude cosine angle, magnitude sine angle, and then I'd add them together. And now, careful. What are they asking for? Oh, just component form. Perfect. So you could have added them together and just been done. You didn't have to go any further. But in word problems, sometimes you might have to go back to the magnitude and direction, which is what we did in class.
What do you mean add them to?
Because going back to our notes, that example that we did, this is how to get components, and then this is how to add components. The resultant is the sum.
You just put it in the calculator.
Yeah, this guy, well, you have to do like terms. So the cosines get added together, the magnitude cosine angles get added, and the magnitude sine angles get added together. Just add it straight down. And then, if they just want components, you just box it and say, okay, cool, I'm done. But if they want even more magnitude, plug it into your A squared plus B squared square root. Direction, plug it into your tangent, inverse. And in our notes, we say consider the picture. This one, that was enough. We were done because it was the first quadrant that we needed. In other pictures, it might be hard. Alex, did I skip over a question?
Number 35, I was confused with the adding the vector addition, the scalar multiplication. Thank you, Sophia, for that.
Oh, and number 35. Actually, no, he wasn't too bad. Sorry, I was looking at 36, and I'm like, oh, did you see it was 0? But sorry. So you, I thought he had said 36, which I thought could be tricky because there was a 0 I. But you guys are doing 35 where there were I's and J's for both. If it helps, Alec, remember that linear combinations can be written as components. So I could rewrite this guy as 1, 1, if that helps. Because it's 1I plus 1J, which this is just an alternative to the side L. The I's and J's don't change anything, it's just another way of writing it. In the book, it's called a linear combination. You're adding horizontal vertical as opposed to this weird, like, ordered pair but not notation.
I just don't know what to multiply them by because they never give us the.
Oh, up here. You have to look at the A and B and C. So A says just adding them. Okay, cool. The horizontal plus horizontal, 3. The vertical plus vertical, -2. So we're just like stacking them. Or we're subtracting, so then we're making the signs. Subtracting, you can make him a negative and him a positive and then add. And then this one you would just do double. Yeah, they were hidden up there in the directions. Anything else that we got stuck on as far as what the question was asking or what was being used to answer it? Megan? 62? 3. Oh, 63 is down here. Okay, as I get 63 ready for us to answer, I'm going to go ahead and get the first word problem up on the board for you guys to try to draw a picture for, / write down the good information for. Now, the nice thing is, the one that I had as grade a second ago, or at least peek at, number 94, that was super short. That's not like this problem, because this problem, I think I gave you an odd that was similar. I think I gave you an odd that was similar, so you could check CalcChat and be able to see if you were on the right track in that. But this one, Megan, it was 63 or 64? 63. But you guys go ahead and get down the key information in this word problem. If I were you, I would. It doesn't have to be gorgeous. I would just go ahead and have like an M, right? Just have an M. You can do like crane 1, crane 2. You're trying to find the tension in each of the cables, and that's actually those little baby vectors that maybe you see. Which we could name like one of them U, one of them V, or you can name them like one R for red and one B for blue. Different ways of naming it, but we're trying to figure out what those vectors are. They're working together to hold up this load. I'm going to go ahead and try to get the picture off to the side so that way I can get Megan's question kind of snuck in here. Okay, I think you guys can see all the important information. Find the magnitude and direction. Okay, don't be confused, or try not to be confused, Megan, by the linear combination form. Remember, like I was just showing Alec, this can be rewritten in the component form. And as soon as we have components, remember this guy can be my A, whereas this guy can be my B. So then when we do this whole find the magnitude and direction, there are actual formulas for this. Like, hey, just take the A and take the B and square and add. So in this case, it'd be 36 plus 36, which is 72. Which there's a 36 whose square root is 6. We could simplify the radical. But then for direction, there's also a formula for tangent inverse of B over A. And B over A, well, that actually ends up being negative 6 over 6, which is tangent inverse of negative 1, which, to be honest, we actually know that that's a unit circle thing. In that tangent inverse of negative 1, that's at a 45 degree. Now, I'm going to go ahead and really quickly, and in our notes we wrote this, look at the picture. I put 6 out and 6 down. So I need to figure out what kind of angle that they want. Because tangent can be, let's see, tangent is positive here and here. So those angles, those quadrants are bad. But these two quadrants could have been fine. It could have been 135, or it could have been negative 45. I guess it could have been 315. I'm going to cancel out the 135 though, because according to my information, you're supposed to go 6 right and 6 down. 6 right and 6 down gets us in this 4th quadrant. And then my just question kind of to myself, but to you also, is which one are we going to choose, the negative angle or the positive angle? And even though the negative angle is smaller, since we're in physics, they'll probably choose, my guess, you guys can double check me, is the positive angle, just because that would be like a normal rotation. But you could have done the negative 45 or the 315. But yeah, just need to look at those linear combinations as really just components, and then you can use your good old school formulas with it. Okay, so now we're looking at these cranes, trying to hold up this load. And there's a lot of math, there's a lot of work going on, kind of, sort of. And there's a lot of unknowns. Because if you guys notice, we know two different angles. We know two different angles, and we know one weight of a load. Now I'm going to go ahead and try to use the book's labeling for the different components, the different pieces. Even though we could use A's and B's, the problem is this red guy is going to have A's and B's, and this blue guy is going to have A's and B's. So I'm going to talk about this red guy as being R1, R2. I'm going to talk about this blue guy. I'll show you this little vector arrow. This blue guy as being B1 and B2. Now we do have angles. The blue guy has an angle of 44.5. And technically this red guy has an angle of 24.3. Now the weird thing is that this red guy is actually, his angle isn't in the first quadrant, and yet they gave us a little baby first quadrant angle. So we're going to have to realize this red guy is going left and then going up in order to get to his vector, whereas the blue guy is going right and is going up, because our angles aren't going to really tell us that since they're both first quadrant angles. We have to realize, well, we could do 180 minus 24 if we wanted to have the signs be all perfect. We can kind of make them ourselves down here. So this red guy, okay, magnitude, cosine angle, and magnitude sine angle. Well, hold on. I don't know his A or B, which means I also don't know his magnitude. Well, that's a bummer. I'm going to go ahead and call that x sub r, because I'm just like, okay, whatever. I don't want to write that thing 1,012 times. But I also don't know this guy's magnitude either. So I'm going to call that x sub 2. And here's why. I can set up this guy's components if only I knew x, if only I knew his magnitude. I could say, okay, I have x sub r cosine of his 24.3 and x sub r sine of 24.3. I'm glad you guys actually asked some of the questions that you did, because that reminds us of the formula that I'm using. Magnitude cosine angle, magnitude sine angle. Now, careful. I'm going to come back to my picture, and I'm going to see that movement left and movement up and say, ooh, this guy needed to go negatively because he needs to go left, and then he's going positively. I can use those first quadrant angles as long as I put in the right signs, so negatives and positives. Now, if I move to the blue guy, I also don't know his magnitude, but I do know his angle to be 44.5. I also don't know his, sorry, he's B. I also don't know his magnitude, but I do know his angle of 44.5 to put in the sun. Now, he's actually positive for both because he's actually moving right and up, so he's okay. And the reason I'm adding these two together is that they're working in tandem to hold that crate, or to be able to lift that crate, to offset that crate. And the one vector they didn't show you was the crate. The crate's trying to go straight down. The crate is actually the one guy that I do know. The crate is the result. He's the resultant. He's the overall what's happening by these two cranes pulling at a certain tension. And the crate is going nowhere horizontally. And vertically, his weight is being offset. And so these two pulling up or pulling away from each other are offsetting that 20,240. I know that even though, okay, when I add these things down here, when I add these two horizontal components and these two vertical components, I actually know what these two need to be. I need these two to equal 0 all the way down. And I need this side to equal 240 when it goes down. So I end up with the following. I end up with negative x sub r cosine of 24.3 plus x sub b.
Would it be negative 2240?
Yeah.
No, but on the initial thing.
Yeah.
No, but you have the answer. The 0, 20,000. Yeah.
Oh, the crate is pulling down, but this is the resultant of the two that are pulling up. So the crate's trying to pull down, but the two are pulling up. So like the tension isn't gravity. Gravity is the tension is offsetting gravity. So their combined force, if I was to move this guy, their combined force is pushing up to offset gravity that's pulling down. Does that make sense? Has to equal 0. And then this other one, I'm going to have the other side. So that's the exact same thing, but with triangles instead. Now, to be honest, guys, I know this is a little rough. Oops, that's a positive. But the nice thing is this is the hardest one because you guys saw the work just a second ago of the other one that was a lot shorter. I just need to show you guys that this is basically an Algebra 2 question with a pre-calculus setup. Because if you guys notice right now, this is a system of equations. That just, it's a system of equations. You have an x and a y and an x and a y that you need to solve with substitution. What do I mean by that? You would get something like, I don't know, let's say this guy, x and b. You would get him by himself. You would add that to the other side, you would divide. And then you would take that entire expression and you would plug in. And then you would have everything in terms of one variable that you would solve for. Which is messy and which is a little bit gross, but technically it's actually just Algebra 2 in the sense of solving with a system of equations. Now guys, what we weren't able to get done were the other 2 word problems, which is what we're going to start with at the very beginning of class tomorrow. Which is honestly a lot easier as far as math. Bummer is we have chapel schedules, and if we didn't, I could have totally gotten to the 2 easier ones. But the other bummer is now we're about a week and a half behind instead of a week. So if you guys don't mind, just as you leave class today, thinking about, can you go tackle the one that's like this one? The system of equations, you don't know components, you're trying to find them. You know the result. Are you willing to come in tomorrow? Just tackle what we need. Tomorrow we're going to finish these 2 word problems. I'm not going to spot check them until Wednesday along with your notes. Which means our test is not going to be this. Anxiety levels are high.
Too high.